All right, so let's talk about an RC circuit. Now, specifically in AC, so we're going to take an alternating source and we're going to connect it to a resistor and a capacitor in series. So our source voltage is changing with time. Our resistor will have some sort of voltage as a function of time. Our capacitor will have some sort of voltage with respect to time. Kirchhoff's loop rule must still apply, must still be satisfied, meaning if we were to add the voltage of the source at a given moment in time plus the value of the resistor's voltage at that given moment in time plus the capacitor at the same moment in time, they would have to add up to be zero. Because if I go around the loop, I can start anywhere I want. I just have to get back to where I started. I will pass those three elements. So their voltages at that moment in time must add to be zero. Now, keep in mind these lowercase v's for the resistor and the capacitor mean the potential difference across the resistor as a function of time, the potential difference across the capacitor as a function of time. Capital values, capital V sub R, capital V sub C, and our EMF naught, these are maximum values. So this would be the max source voltage, this would be the max voltage drop across the resistor, this would be the max voltage drop across the capacitor. It turns out this will not equal zero. And the reason why is because they will not have maximum values at the same moment in time. So totally Kirchhoff's loop rule applies at any one given moment in time. That is still totally true. But max values don't occur at the same time. That's why we can't say the loop rule is valid in terms of these maximum values. Now, to talk about the overall current that's going to end up flowing one direction and then the other, back and forth, this is where the phasors come into play. In series, if you remember having resistors in series, they had to have the same amount of current flowing through them. Capacitors in series, they had to have the same amount of charge that has accumulated on the plates. Since the rate at which our capacitor is charging and discharging is the current, we know that I, current, has to be the same everywhere at any one given moment in time. So I guess I should say our lowercase r, I, is the same everywhere. Now I'm going to call this IRC because now we're putting a resistor and a capacitor together. The current through the resistor has to be the current everywhere at any one given moment in time. Phasors, our phasor diagram. I am going to just choose a moment in time. I can draw this at any moment in time. A phasor, remember, is just a vector. The length of the vector represents the maximum value, and those vectors rotate based off of this omega t of the source. So when I draw a phasor diagram, I'm drawing it for one specific moment in time, and I can choose that time. So I'm going to choose a moment in time that the current through the circuit is a maximum positive value. So this moment in time, when I draw the phasor itself, the length of this phasor represents that peak current, that maximum value of current that flows in the circuit. Because I have drawn it at the moment in time where we have a peak current, then this X component is also the instantaneous value. I choose to be on the x-axis just to simplify my vector addition. We're going to be adding vectors because phasors are vectors that rotate. When we look at our phasors at one specific moment in time, we can just use regular vector addition. So I'm just trying to simplify the vector addition I will be doing. Thinking of resistors. Resistors, the current through the resistor was in phase with the voltage across the resistor. Capacitors, the current flowing in the circuit that had the capacitor was 90 degrees ahead of the voltage drop across the capacitor. So our phasor diagram needs to represent this. The reason I'm drawing the current first is because we have these in series and I know they have to have the same current. Okay, what I want to do next is draw a phasor that represents capital V sub R, meaning the maximum value the resistor's voltage would be. And then I want to draw another phasor that represents capital V sub C, meaning the peak value or maximum value of the voltage across the capacitor. Since the resistor is in phase with the current, I would draw my VR also along this x-axis, meaning a moment in time when the instantaneous voltage across the resistor is a maximum. Ultimately, what's important here is that the current phasor and the voltage phasor for this resistor they lie along the same line. That's what represents they are in phase. Now the capacitor's phasor, though, the current is ahead of the capacitor. Sorry, the current is ahead of the voltage by 90 degrees. So current being ahead of the voltage by 90 degrees means the capacitor's phasor points down this way. Now the length of it depends upon the circuit. I'm just drawing a length. The length of this capacitor's voltage represents the maximum value. At this exact moment in time, though, the resistor's voltage is maximum. The capacitor's voltage at this moment would be 0 because there is no x component of this vector. Okay. To represent Kirchhoff's loop rule, we simply add the voltage phasors, and we have to add them vectorially. The phasors are vectors. We've drawn them at this exact moment in time, and so vector addition is what we need to do to relate this back to the source voltage. Well, if you recall, with vectors, we can add them tip to tail. So I can either take VC and add VR, or I can take the original VR and add VC, whichever. The result starts where those vectors started and points all the way out to where that second vector ends. This vector represents the maximum source voltage. Okay. That comes from this loop rule. By adding these phasors at one moment in time, we get the result of the source voltage. It turns out this source voltage is out of phase from the current. It's not out of phase by 90 degrees. We can say the current in this RC circuit is out of phase with the source voltage by phi, that phase angle. Okay. To put this into a circuit as a whole and to look at the current and so forth, we can say that the source voltage must equal, well, let me approach this differently, actually. Let's just set up my equation here. I have a triangle now. This source voltage maximum value is the hypotenuse of a triangle here that has one side being VR and the other side being VC. So Pythagorean theorem, I could say the source voltage squared, the hypotenuse squared, is equal to the resistor's peak voltage squared plus the capacitor's peak voltage squared. That's just Pythagorean theorem. One side squared of my triangle plus the other side squared has to equal hypotenuse squared. Okay. My triangle is right here that I'm looking at the moment. I'm choosing that one because I drew my phi in that triangle. So to talk about phi, I'm just going to use this triangle. All right, so this source voltage squared is going to equal, well, we know the capital V, if we look at the equation specific to the resistor. So when we talked about resistors alone, we said that capital V was the current through the resistor times the resistance. So I can plug that in and then square it because of the Pythagorean theorem. For the capacitor, the maximum current times X sub C would represent V sub C. Now, technically in the test notes, we have the capital IR is capital V sub R over resistance, and capital IC is VC over XC. I'm just solving both of those for V and plugging them in their appropriate space. Now, because we have these in series, the IR is the same thing as what we mean by IC. This is our IRC that I mentioned before. And that's because they're in series. In series, they must have the same current. If that's the case, I can call them both the current in this RC circuit, and I can factor them out. If I take and solve for IRC squared, I would be bringing over this quantity of R squared plus XC squared. And now I want to take the square root of everything. Well, on the numerator, I can just take the square root and be left with that maximum source voltage. But I cannot square these individually, so I have to write this as the square root of that whole quantity. This represents the maximum value, or the maximum amount, well, not amount, the max value of the current that flows in this RC circuit. So the maximum value or peak value. The peak value depends upon the max source voltage, and it depends upon the resistor value and the XC value. XC is the capacitive reactance, which is 1 over omega C. We have that in the test notes. So if I wanted now the voltage drop across the resistor, like the peak voltage drop across the resistor, that would be the current that flows through it in this circuit, which is this IRC, times R. So if I take I over here that we just came up with and multiply it by R, I find that the resistor's voltage will be the source voltage times the resistor over this square root of R squared plus XC squared. When you look on the test notes, it's actually on the second page for this chapter. It says RC, the heading for it is RC filter circuits. We simply mean an RC series circuit, so a resistor and a capacitor connected in series to our voltage source. The peak voltage across the resistor is determined with this equation. We do not need to find this equation again. The capacitor, recall, is the current flowing through it times its capacitive reactance. Well, the same current's flowing through it, so if we just plug in that current, and then multiply by XC, this will give us the peak value of the voltage across the capacitor. Now, both of these will vary if the oscillation rate of the source varies. And that's because XC will change based off of frequency. Omega is angular frequency. So that's just a conversion of units from cycles per second to radians per second. So if we change even just the frequency of the source, that is going to change the current and thus the voltage across either element. Now, in terms of filter circuits, let me actually grab a picture from our text. So this graph shows us how the voltage for the resistor, the peak value, and the voltage for the capacitor are changing based off of the frequency of the source. So these values on the horizontal axis are representing the angular frequency or possible angular frequencies of the source, the alternating source. If we change omega, that changes our voltages, and that's because XC changes. So this top graph, this top graph represents V sub C. V sub C, the peak voltage across the capacitor gets smaller and smaller and smaller as omega gets bigger and bigger and bigger. It's not a linear function because we have xc in the numerator and in the denominator when we're talking about V sub C. But as angular frequency goes up, that voltage will go down for the capacitor. The resistor's voltage, though, goes up because, or as that frequency increases as well. And that's because the resistor's voltage over here on the left, our equation, xc, if omega gets bigger, xc gets smaller, and xc is only in the denominator there. So the resistor and capacitor, their voltages, their peak value of voltage changes based off of the angular frequency of the source. Now there's this point right here where VR and VC are equal. That point, the frequency, the angular frequency that occurs and causes them to have the same voltage is called this crossover. That's where those graphs cross. So we know VR is the peak value. These capital letters mean the peak value. The peak voltage will be that peak current times resistance. The peak voltage for the capacitor will be the peak current times its capacitive reactance. But again, we're specifically talking about them in terms of being in series. So this crossover frequency represents when the resistor's value is equal to the capacitive reactance. Well, we know capacitive reactance is 1 over omega c. So this crossover angular frequency, specifically, if I solve for it, will be 1 over RC. Now be careful in this chapter because we do get a little, I don't know if lazy is the right term, of leaving out the word angular. Crossover frequency, we saw it written just right there. It's specifically, though, an angular frequency because it's labeled as omega. Omega is always radians per second. So just be careful. If you see omega, that means the units will be radians per second. And if you want to get it to hertz or cycles per second, that's just a unit conversion between the two. Now, in terms of calling these filter circuits, let me grab one more picture to show you. All right, so jumping again, we have in both cases here, both pictures, we have a resistor and capacitor connected in series. If we followed the path, we have the source, the resistor, the capacitor, back to the source up here, source, capacitor, resistor, back to the source down here. So these are both representative of an RC circuit. They're both in series. The order doesn't matter in series. They changed the order, though, to talk about these V outs. If we connect leads across the capacitor specifically and measure the voltage across the capacitor, we have what's called a low-pass filter. When you are constructing an electrical circuit, which you may or may never do, for example, an EKG, also sometimes known as an ECG, electrocardiogram. You're connecting a circuit to a person's chest. So you have the person's chest, their neck, their arms, their chest, and they put these leads on you in different spots, essentially surrounding your heart. That's a beautiful heart right there. That doesn't in any way represent the right shape. So what's happening is these leads are connected to a monitor. Our hearts are beating because of electrical pulses. So there's actual currents, electrical currents that flow through our hearts and cause them to beat. So these leads, when we connect them to the equipment, we want to be able to see the heartbeat on the monitor. Well, anytime we have electrical equipment in a room that has other electrical equipment, these sensors are going to pick up frequencies from everything, essentially. And so a filter is needed, which conveniently this monitor has already been built for the doctors, whoever's using it. But the monitor has a filter already built in. Now, the difference between a low-pass filter and a high-pass filter is essentially the frequencies that they transmit. So a low-pass filter will transmit frequencies that are smaller than the crossover frequency, and they will block. So transmit means lets through. They will block frequencies. They will not let through frequencies that are greater than the crossover. And then the high pass is just opposite. It lets through higher frequencies and blocks lower frequencies. So how the frequencies you want to detect compare to the unwanted frequencies is what determines if you were to actually build this monitoring system, that would be based off of comparing these frequencies. So the unwanted frequencies from other equipment here is going to be 60 hertz because our wall outlets operate at 60 hertz. And so we need to block frequencies that are 60 hertz, but let or transmit frequencies of the heart. I don't recall if the frequencies of the heart are better or higher or lower than the crossover frequency. Higher or lower than 60 hertz, essentially. In grad school, we had to build a EKG monitor, which was really pretty dang cool. We had an interface where we had to build the circuitry, and we had to decide which filter was appropriate and build that filter. And then we got to try it out on ourselves. Put the leads on our chest and measure and see if we got the system and the pattern we wanted. We also got to build an EMG, which measures muscle movement. And the same idea was there. We had to rule out and get rid of and block unwanted frequencies and allow the transmission of the frequencies that would be detected from the muscle movement. And it's been way too long since I was in grad school, so I don't remember which one was higher or lower, but I do specifically remember needing to filter out the unwanted frequencies. There are, of course, many more applications, and I am in no way testing your understanding of building an actual filter. What I want you to understand, though, are our equations over here that we came up with. These equations are on the test notes. You don't need to derive them again. They're available. This is on the test notes. So these equations are available to us. So what you need to be able to recognize in the homework or on the test would be that you have an RC circuit. All that ultimately means is that we somehow have a resistor and capacitor connected in series. That's the connection we're specifically making. So if they're connected in series to this alternating source, those equations we derived are valid. And so those would be the equations we would use to solve our problems. I like to mention the filters though, our book does as well, but it is interesting in terms of building circuits and just the concept behind it. We'll talk inductors next as well and look at putting all three together.